Hi everybody, in this example you would like to discuss about some torsional issue. On the left side, you have a hollow shaft. On the right side, you have a solid shaft. Here you have the same condition. The first condition is length is same, and the same material, and on the same torque we have same torque. Then we would like to calculate tau. Tau is shear stress, and phi change of angle, and weight and strength to weight ratio. We would like to find it. Okay, in order to find that, we would like to have some related concepts. Or we must first understand what's the structure. If you think about this kind of structure, this one is cylinder, just like right side one. Radius is r, length is l, and torque is given, let's say t. Okay, in this case we can apply the formula phi equals what? G I P, polar moment of inertia, and torque T, and L. Phi is given in radian. Okay, well, we can apply tau max, maximum shear stress equals IP, polar moment of inertia, TR. In the case of a cylinder, polar moment of inertia IP equals integral A r squared dA, or phi over 32 d exponential 4. Okay, this is available. If this one has self weight density gamma, and cross-sectional area is A, let's say cross-sectional area. Total weight is what? And volume is AL. This one is volume. And to the volume, when you multiply gamma, then you have total weight. Okay. Gamma is weight density. Okay. This kind of prior knowledge is required to solve this problem. At first, let's think about polar moment of inertia in the case of hollow one. This one is hollow one, this one is solid one. Okay, when you apply this formula, and 5 over 4, 32 outside R 4 minus inside, sorry, not R4, in this case D4, actually 2R 4, when you're aware of D4. Then in this case inside diameter is 0.6 R, that's why 1.2 R 4. Then finally you can get this kind of value in the case of hollow shaft, polar moment of inertia. In the case of solid shaft, this kind of one, phi over 32 and D 2R and 4, 2R and 4. And polar moment of inertia can be calculated like this one, and finally you can get this one. Okay, we've got this kind of relationship, polar moment of inertia in the case of hollow one, and solid one you can have this kind of relationship. Okay, let's go further. We would like to calculate the ratio of maximum shear stress. Maximum shear stress is given by like this one. And in the case of hollow one, tau max TR over polar moment of inertia in the case of hollow one. and we have ratio tau h over tau s, and when you calculate this one, then tr over I p hollow 1, and this is divided by tr over I p s. Then you can delete this one, then you can finally have this kind of relationship. Inversely you have a relationship. And next one, change of angle. Ratio change of angle. Change of angle is what? This value, TL GIP. All the same, TL is same, and at the same time we have same relationship with this one. And phi, let's say phi in the case of hollow one, and phi over solid one, and the same relationship like this one, because both of them is same, and then finally you can get same value, like ratio of maximum shear stress. Okay, let's move on to another one, weight. In the case of weight, weight is given like this one: cross-sectional area, and gamma and L. When you consider cross-sectional area here, cross-sectional area A and L is the same. That's why not A is different. So sorry, gamma and L is the same. Gamma. Then in the case of hollow one, A is 5 over 4. The outside 2r squared minus inside 1.2, sorry, r squared. Sorry, here 5 and not 5 of something wrong. This is not correct. I mixed up. Instead of A equals 5r squared, not this one, 5r squared minus inside the 5, r is what? 0.6 r squared. This one is AH in the case of hollow. Then you can calculate finally this one. And when you find the ratio between hollow one over the solid one, it is directly related to cross-sectional area. This ratio is the same as AH over AS. This one is 0.64. Okay, next we would like to calculate strength to weight ratio. Okay, finally SH and SS, strength to weight ratio. In order to find that, final value would be strength to weight ratio is like this one. Weight. Okay. TH. We would like to calculate firstly TH. How we can calculate? There are different ways to calculate it. We go back to here again. If you know tau max, we know IP value and R, then you can calculate T, this one, this one. Or you can apply this principle again. If you know phi value, you can calculate also T max value. But here we would like to apply this relation, tau max equals IP TR over IP, this relationship, because we know tau max. In the case of this one, T max, tau max and this one is IP over R. Okay, IP over tau max still there, and IP we've calculated in the case of hollow shaft is given by here, and R, of course large R is given. Then finally, let's say R, then finally we can get this one. In the similar method, tau max also given like this one. I polar moment of, in the case of S, is divided by R. Then you can have this relationship. And weight density is given like this one, comma, weight density is given like this one. And self-weight, total weight, in the case of hollow shaft, A, cross-sectional area, I've already told you, A is multiplied by L and comma. And L and comma is given. In the case of WS as well, A, S, L, comma is the same. And we would like to calculate the ratio, strength to weight. Strength to weight is given like this one. We calculated this value on the left side, TH. And we also have self-weight, weight density, weight density. When you apply this one, self-weight is given by this one. When you apply this ratio, then finally you can get this value. In the case as well, when you apply, in this case here on the denominator, and here when you apply TS value, then finally you can get this kind of value. Okay, in this value we have some different kind of characteristics we've found, but mainly it was from this relationship. Firstly, when you think of this kind of cylindrical bar, okay, cross-section area is A, and torque T is given like this one. Radius is given. Be careful about radius. We normally deal with diameter like this one. Okay, we have the relationship phi. Change of angle is given by this one, and maximum shear stress has this kind of relationship. Of course, polar moment of inertia in the case of solid one is like this one, solid cylinder is like this one, or in the case of polar moment of inertia equals phi of, in the case of hollow one, 32, outside diameter minus inside diameter, density, in the case of hollow shaft, in the case of hollow shaft. And another thing is self-weight is given by weight density is multiplied by volume. Then you can calculate the self-weight. Okay, when you apply this kind of relationships, then we can solve the required solution in this problem. Here on the left side we have hollow one, right side solid one, and same length, same material, and the same torque, etc. And this value we would like to calculate it. And firstly maybe you can calculate polar moment of inertia, hollow one, and polar moment of inertia in the solid one. And next one, you can calculate ratio of maximum shear stress and beta 2 automatically. And finally you can apply this value to weights. Weight can be calculated like this one, and strength to weight ratio is given by this relationship. Strength you can have this relationship, then you can calculate it. When you introduce weight density like this one, okay, you can calculate weight density And finally, strength to weight ratio is calculated by this formula, like this one. And when you finally introduce weight density concepts and this value, strength to weight ratio SH is given by both relationships. Okay, that's for example 3.3. Thank you.